Welcome to the SAE-VIT podcast. I'm your host, Jatan. Today, we aren't discussing a change in fuel. We are discussing a change in India's destiny. We are talking about the E20 fuel mandate. Sanjeev, before we get into the crux of the topic, why is the government treating this like a wartime emergency?
Because it is an economic war, in my opinion. India is, currently the world's third largest oil consumer, importing more than 85% of its crude oil needs. So we are at the mercy of global oil prices, the OPEC decision, and the shipping instability for now. But when the oil prices spike, the Indian rupee takes a hit, the inflation goes up, and every middle class family feels it at the pump and in their kitchen bills.
The E20 is not just an environment story, it's a balance of payment story.
Exactly. By fast tracking E20, the government is essentially saying that we want to produce our own energy on our own soil from our own farms in our own distilleries. Every liter of ethanol blended into petrol is a little less foreign exchange going out of the country.
No, numbers are staggering. We're talking about diverting around 6 million tons of sugar annually to ethanol production, plus grains like rice and maize in surplus years.
Right, and it's not just sugar anymore. The spotlight has shifted to second generation or 2G ethanol, as people say. This is made from the agriculture residues like rice, straw, corn cobs, cotton stalks, and even damaged food grains that cannot be sold for human consumption. Right, but instead of farmers burning stubble and causing smog in Delhi, maybe they can sell the waste to a distillery and earn from what was earlier a liability.
So it sounds like more of a circular economic dream, waste to wealth, pollution to profit.
It is on paper, right? You get multiple good factors out of this: rural income through an assured market for residues, or reduced crude imports and better energy security, and also lowering the life cycle of CO2 emissions compared to pure petrol. But every good engineering solutions has constraints and trade-offs. Definitely.
So let's put on the devil's advocate hat. We are a country that still faces food security issues. Is it wise to turn food into fuel?
It is definitely a massive ethical debate, right? The political line from the government is only surplus grains and the non edible parts like molasses are used, and the food security is not compromised. But markets do not behave ethically, they respond to price signals. So, as the demand for E20 grows and ethanol price stabilizes, farmers might be tempted to shift from pulses or coarse cereals to sugarcane or maize just because the buying contracts from distilleries like look safer.
So from the same field that could have grown dal for a hostel mess, might end up growing fuel for a hatchback?
Exactly. If not managed carefully, that can distort cropping patterns, stress groundwater and sugarcane belts, and indirectly increase food prices. So the challenge is not one or two, multiple. Maybe say it would be to push ethanol from genuine waste and residues, or grain-based ethanol so it doesn't eat into food buffers, or also we could use policy levers like MSP and procurement to prevent a blind rush into fuel crops.
So the E20 story is a balancing act. Energy independence on one side, food and water security on the other.
Yeah. So that's what makes this not just a mechanical engineering topic, but also a public policy and an ethics topic.
Now let's more move on to the molecular battlefield. Let's move from the fields to the fuel tank. Sanjeev, you've mentioned hygroscopy before, but let's really break it down for our student engineers. What is happening at a molecular level when E20 meets a humid Chennai afternoon?
So if you see, ethanol is a polar molecule, and petrol is mostly non-polar hydrocarbons. So under normal condition, they form a homogeneous mixture, and when blended as E10 or E20. But water is also polar. So what happens is the ethanol molecules has that hydroxyl group, which is like a tiny magnet for the water molecules.
So, in a hot coastal city with humid air, the fuel literally drinks water from the atmosphere.
Exactly. If the fuel system is vented or the tank cap is not properly sealed, moisture can diffuse in, and especially this can happen if the vehicle sits idle for days. Over time, ethanol absorbs this water until the mixture hits a threshold.
And once it grabs that water, what's the point of no return?
That is officially termed as the saturation point, right? So once the fuel reaches roughly 0.5% water content, the affinity between petrol and ethanol breaks down. What happens is the ethanol and water decide, like no, they like each other more than they like petrol. So and they separate into a heavier milky layer that sinks to the bottom of the tank.
I've heard it's called the slug by the mechanics.
It is. I mean, imagine a slug of water-rich ethanol sitting right at the pickup point of your fuel pump. The pump is a bottom feeder, so when you crank the engine after a long park, the slug is the first thing to hit your injectors or the carburetor jets. Since the water doesn't compress or burn, what you'll get is nothing but a hard starting or no start at all. Maybe massive misfires as well. So in worst case, the hydrolock if a cylinder fills with liquid.
But that is just the mechanical side. You mentioned galvanic corrosion earlier as well.
Yeah, so the water and ethanol mix is conductive, right? So when it sits against bare metal like a steel tank or an unprotected aluminum surface, it can create tiny electrochemical cells. So it's basically like multiple small batteries eating away at the metal, which is galvanic corrosion. So over months and years, this can maybe pit the wall or strip protective coatings. And no, it can also generate rust particles that later on travel downstream and clog the filters and injectors and whatnot.
So what does it basically mean for the average owner? Never let the car sit?
Ideally, so practically, if I have to say, maybe avoid storing E20 in vehicles for very long durations. Keep overturn high if possible, and also keep tanks closer to full or reduce the air volume, and hence the moisture in the tank, which is have to keep it as minimal as possible, and also make sure caps and seals are in good condition to minimize the vapor exchange that happens. So that kind of everyday behavior change is definitely as important as any fancy material upgrade to the vehicle.
Okay, let's move on to material science about elastomers and metals. Let's talk about the hardware. If I'm looking at an engine from 2014 versus 24, what are the literal physical differences?
The key word we're looking for here is compatibility. Earlier, most fuel system elastomers were nitrile rubber (NBR), but ethanol attacks NBR by swelling it, leaching out plasticizers, and then eventually making it hard and brittle. So, seal designed for tight dimensions might swell by 20 to 30%, lose its elasticity, then crack and start leaking.
So your fuel-proof hose from 2012 suddenly becomes a slow drip waiting to happen.
Correct. The modern E20 compliant vehicles use, fluoroelastomers like Vitcon, maybe also known as, if you have heard, FKM or similar for O-rings and hoses. Even Teflon liners inside the fuel lines and some in-tank components are used, while upgraded sealants and coatings that do not soften or dissolve in ethanol are things used nowadays.
What about the metals? I've seen reports of this white rust inside carburetors.
Yeah, that white rust, that's the aluminum corrosion. Now, ethanol can react with aluminum and its oxiding layer, forming aluminum alkoxides in white powdery corrosion products. These deposits clog fine jets and passage in carburetors and can stick in pintles and injectors. So to counter that, new engines use like stainless steel fuel rails and lines, and they also use better ionized or coated aluminum parts, and also the hardened valve seats and like compatible injector internals.
For a legacy owner, is there a retrofit kit? Can I just swap my hoses and be safe?
Swapping hoses to Viton is a good first step for safety, especially against the leaks in the engine bay. But you definitely have to consider other factors like you cannot easily change the internal rubber in the fuel pump. You cannot recoat the inside of an old steel tank at home, and you definitely cannot change all the tiny seals inside the injectors or carburetors economically. That's why this transition is can also be described as a survival game for the old vehicles. Some will cope, some will slowly develop leaks, rough running, or maybe fuel system failures.
This explains why some OEMs publicly say E20 is safe, but quietly issue advisories for older models.
Exactly. For vehicles designed before the E20 was in the rule book, Many manufacturers now say use at your own risk, or like put limits like short term use only, because the legacy materials were never validated for this chemistry.
Okay, so let's move on to ECU mapping and the lean danger. Let's get into the brain of the car, the ECU. We know that E20 has more oxygen in the fuel. How does the car actually know it's burning ethanol?
In advanced flex fuel cars, there's a dedicated sensor that measures the fuel's dielectric constant and the temperature to infer the ethanol percentage. So what happens is it sends a real-time ethanol content signal to the ECU. So timing, fueling, and sometimes even the boost targets are adjusted to the fly.
But that's the Brazilian flex fuel story. One tank, many possible blends.
Yeah, sure. Like you said, the Brazilians' experience shows how flex fuel technology can become mainstream. The engine's designed from day one to handle any form of pure petrol to high ethanol blends, plus a fueling network that clearly labels the pumps and prices. In India, but most mass market cars don't have that dedicated flex sensor. They just go with something simpler.
Is it the oxygen sensor in the exhaust?
Exactly. So the ECU sprays you a fuel based on its base map, then checks the exhaust mixing the O2 sensor. So if it detects a lean mixture, too much, which is too much oxygen, it detects injector pulse width. So that's a closed loop feedback.
But ethanol wants more fuel to reach stoichiometry, right?
Yes. So ethanol's stoichiometric air fuel ratio is lower than petrol's. So E20 effectively needs more fuel for the same air mass to avoid going lean. So the ECU uses short-term fuel trim, also known as the STFT, and long-term fuel trim, which goes by LTFT, to compensate. So on older ECUs, that adjustment window may be only around 10 to 15%, while full E20 may demand closer to 20% or more fuel in some conditions.
So you basically hit this ceiling of the trim window.
Correct. Once the required correction goes beyond what this ECU allows, the mixture still stays lean, right? The exhaust gas temperatures climb, the exhaust valve and the catalytic converters are stressed, and you may see a check engine light and risk damage to the plugs and valves over time eventually.
And the driver just experiences it as car feels weak, car feels hot, MIL lamp is on.
Exactly. So the newer E20 calibrated cars, right? The base maps, injectors, and sometimes the compression ratio are all turned about this blend. So they can even gain a bit of performance and emission benefits with no reliable penalty. On the older hardware, though, the same fuel can become a stress test.
Let's now move on to the aftermarket and the experience side. Brazil has been doing this since the 70s. What did they learn that we are still figuring out?
There are three big lessons, I would say. The first thing would be you need engines designed as flex fuel from the start, right? And then you need fuel pumps and infrastructure that can handle multiple blends reliably. And you'll also need pricing that respects the energy content. So if ethanol gives less mileage, it must be cheaper per kilometer. And ethanol only and the later flex fuel cars in Brazil were engineered with different material, compression ratios, and cold start strategies to suit the ethanol's properties.
The different pricing is required. Like if you lose 20% mileage, the fuel must be about 20% cheaper so that the cost per kilometer is similar.
Definitely, totally agree on that one. Because, like you said, if E20 or higher blends are priced at almost same as the older petrol, then the customer feels punished at the pump, right? Because more frequent refills, similar rupees per liter, that creates a friction and sometimes backlash, especially when people perceive performance or mileage drops in old vehicles.
And what about the aftermarket? I've seen ethanol converters or flex fuel kits online. Are they legit?
Most budget kits are piggyback devices, I would say. They intercept the injector signals and fool the ECU into opening them longer, adding more fuel so that the engine doesn't run lean. So maybe they can reduce the risk of overheating and detonation, and also up to an extent maybe improve the drivability on higher ethanol blends. But they definitely cannot upgrade do not upgrade the rubber hoses or the tank coatings, and they definitely do not protect against long-term corrosion as well. and they are rarely validated to the OEM durability standards.
They're like giving a patient more food but ignoring the fact that the arteries are still clogged.
It's a perfect analogy. So unless a kit which comes with proper material upgrade and it is tested across the Indian conditions, the heat, humidity, traffic, low speed duty cycles, definitely is not a magic pill.
Let's move on to the policy side, the consumer side. On paper, the E20 roadmap promises reduced imports, better farmer incomes, and lower CO2. On the ground, we have confused consumers, legacy vehicles, and a fast rollout. Where do you stand? What was the transition too quick?
The timeline was aggressive, I would say, in my opinion, because the target of 20% blending was advanced from 2030 to around 2025 26. And India has effectively rolled out the E20 nationwide right now, much earlier than many expected. So the upside is clear that foreign exchange savings in billions, a stronger rural ethanol industry, and a signaling that India means business on the energy security. But the cost is being paid is the legacy vehicles that were never designed for it, and the workshops crumbling to understand the new failure modes, and definitely the customers who feel that they were not adequately informed or given choices regarding this.
If for a student engineer listening to this, where is the opportunity?
Everywhere, I'd say, from the point of materials, better low cost coatings, ethanol resistant elastomers, and retrofit friendly tank liners for older vehicles, like you had mentioned before. So that is one. And even the sensors and ECUs, right? Affordable flex fuel sensing, smarter ECUs that can safely adapt to maybe wide ethanol range in the Indian conditions. And also in the process and policy factors, smarter logistics for collecting agri waste, better life cycle analysis tools, or maybe just clear communication, consumer communication. So if the older fleet is being pushed out, there is also opportunity in designing the retrofit solutions that are genuinely safe and certified, and maybe not just the DIY hacks that exist right now.
Now that's a powerful message. As engineers, our job is not to complain about constraints, but to design around them.
Exactly. So the era of pure petrol is effectively over, we could say, and the era of biomobility, where carbon comes from recent plants rather than million-year-old fossils, is here.
Thank you, Sanjeev, for this marathon session, right from the sugarcane fields to the ECU maps and the ethics classroom. To our listeners, if you're driving an older car, get your fuel system checked. Keep an eye on those hoses and listen to what your engine is telling you.
And if you're an engineer, this is your playground. So from material labs to policy think tanks, there is space to innovate at every link in this chain.
That's it for this episode of the SAE-VIT podcast. Stay curious, stay oily, and keep your fuel lines fresh.
Catch you all in the next one. Thank you for watching this video, guys. Bye bye.
Bye bye.